Okay, we're going to be talking about relative rates of growth. And what does this mean? This means that we're comparing functions and how fast they grow with respect to each other. So in different fields like math, computer science, engineering, it's often important to see how functions behave in comparison in terms of their growth. Normally, exponential functions, and not really normally, but this is always true, an exponential function will grow faster, let's say, than a logarithmic function. Okay, but what we're going to do is we're going to apply limits. Okay, we're going to apply limits in order to compare how fast one function grows in relation to another. Okay, so let's take a look here, and we're going to say that a function f grows faster than g if we take the limit as x approaches infinity, if the limit evaluates to be infinity. All right. Equivalently, we can say that g grows slower than f as we take the limit of x approaching infinity if the limit evaluates to be 0. All right. And if the two functions happen to grow at the same rate, what we will see is that we will have a finite and positive limit. What that means is a number, a definite number. Suppose we find the limit to be 2 or 3, a positive number that ends, that's non-repeating. So finite, positive. All right, so let's go ahead and take a look here at number 6. We're going to take the limit as x approaches infinity of e to the x over x squared. So you might look at this and say, well, how would I evaluate this limit? Well, I would tell you that the best approach for this is probably to apply L'Hopital's rule. And if you recall, L'Hopital's rule tells you that you take the derivative and you'll take it successively until you can evaluate it to see what exactly the limit may be. So let's take a look here at this limit. I'm going to take the derivative. Now the derivative of e to the x is itself e to the x, but the x squared becomes 2x. We still can't, plug in infinity. We can't evaluate the limit because it's still indeterminate. We have an infinity over infinity scenario. So we're going to take L'Hopital and apply it one more time. All right. And let's see what we get. We get the limit as x approaches infinity of what? Well, again, it's going to be e to the x, in this case over 2. Now we can no longer take the derivative. Now we can evaluate this, but think about it this way. This right here would be e to the infinity, a huge number, divided by 2. So what this limit ends up being itself is infinity, okay? The limit in this case, doesn't exist. All right, so what we can say here, if we're comparing e to the x to x squared, is that because of this result, f grows faster than g. In this case, e to the x grows faster than x squared. All right, so that's the comparison that we can make. All right, so that's the answer there. All right, now let's take a look at the next one, number 7. We have the limit as x approaches infinity of 3 to the x over 2 to the power x. Well, I'm going to not take the derivative. There's no need. This one I think can be evaluated. We just have to rethink the way that it looks. So let's take a look at this. We end up with 3 halves to the power x because 3 and 2 are both being raised to the x power. Well, this is 3 halves, which is a number greater than 1, to the infinity power, if you think about it. Okay, so in this case, we get infinity again. So the answer here, all right, and it should be pretty intuitive, is that 3 to the x grows faster than 2 to the x. And think about that for a second. It makes sense. 3 to the 0 is 1. 2 to the 0 is 1. So they're at the same level there. 3 to the first is 3. 2 to the first is 2. 3 is bigger. 3 to the second is 9. 2 to the second is 4. Again, the power of 3 is bigger. So it should make some sense there, intuitively. All right, let's take a look at number 8 here. The limit as x approaches infinity of x squared over the natural log of x. So this one's an interesting one because we don't know. which one grows faster. Now, normally I'd say it's probably going to be the x square, but let's prove it. Only because of the statement I made at the very beginning. An exponential function, this one's not exponential, all right, x square, but exponentials grow faster than logarithms, and I'd imagine that a polynomial would grow faster than a logarithmic. So let's see, let's apply L'Hopital's rule in order to get this done. All right, we have the limit as x approaches infinity. Let's take the derivative 2x over derivative of natural log being 1 over x, and we can rewrite this. This becomes the limit as x approaches infinity of 2x squared, because this is 2x multiplied by x over 1. All right, keep the first, flip the second, change the sign from division to multiplication. Well, when you evaluate this limit, you end up getting, yet again, infinity. All right, so it's pretty clear then that x squared grows faster than the natural log function. All right, so just keep that in mind. That's how we would do it. All right, one more example here. We're comparing, in this case, the natural log of x to x to the 1 over n power. All right, so this is kind of like a general, like a root power, if you will, like a root. We're going to compare. We're going to use, again, L'Hopital's rule, because we need to do that in order to evaluate this limit. We're using n, all right, as some degree, and we're looking at a power, or x to a certain power, and the natural log of x. Let's see. The limit as x approaches infinity. I know I have 1 over x, and then the bottom, the denominator, is just a power rule problem. Bring down the power, x to the 1 over n. 1 over n comes down. X to the power 1 over n minus 1. All right, x to the power 1 over n minus 1. All right, what does that look like? Well, we can simplify this with a little bit of algebra. And what does that look like again? Let's see. All right, we end up with 1 over n. All right, the 1 over x is really an x to the first power, or x to the minus 1, but it's in the denominator. So we end up with a plus 1 scenario here down here, leaving us with x to the 1 over n power. Okay, well, think about it. Okay, think about it. 1 over n, x to the 1 over n is in the denominator. It's a power. Okay, it's a variable with raised to some power, some degree, but we're plugging in infinity in here. Actually, in here for x. Okay, we're plugging in infinity for x. All right, and I say that very loosely. If you have $1 and you're dividing it by infinity to some power, any power, and it's a root, you're still going to get infinity. You end up with the case of 1 divided by infinity. You have $1 divided by 1 trillion people. How much does each person get? Relatively nothing. 0, in other words. So because this limit evaluates to 0, we then say, well, the natural log of x, okay, the natural log of x what? Well, look at this rule right here. It grows slower. ln of x grows slower than x to the 1 over n. And that's for any value of n, really. So that's what's going on there. That's the answer for this problem. Okay, so again, L'Hopital's rule came into play, but really it's all a matter of evaluating the limit as x approaches infinity, and that's the same case for all of these problems here. So again, we're talking about relative rates of growth. It's an application of limits, okay? So we're comparing two functions, in other words, and how fast they grow. As always, I hope this video was helpful, and remember, like and subscribe.